Hello, everyone. In the last class, we just learn this important and very useful mechanism called semaphores. So with semaphores, we can solve lots of synchronization problems and mutual exclusion problems. And we also illustrate how to use the semaphores to solve the typical IPC problem, which is the problem of producer and consumer problems. We have three semaphores one semaphore is mutex, which is used to control the access to the critical region, because the producer and consumers, they need to share this fixed sized buffer, and some need to put new items in the buffer, and some needs to take the items out of the buffer. So there is only one processes which can use the buffer at the same time. So we use one semaphore called mutex to control the access to that critical region. And also we use another two semaphores. One is called empty and one is called full, which just represents the available items in the buffer and the available free slots to put some new items into the buffer. So you can see from this example, the semaphores have can provide some power to solve kinds of similar synchronization or mutual exclusion problems. And in this class, I need you to do some exercises on process states and semaphores, because after we learn all of these stuff, these two parts are very important for this course. So before we take these exercises, I'm gonna give you a brief review about these two concepts. So first, about the process states, you can see there are three basic states for any process. Also, they might have the new and exit states and maybe some suspend states. But here we just need to focus on these three core states. If we say this process is in the running state, it means this process is now using the CPU. And if the process is in the ready state, it means this process is not in CPU, but it's how to say, it's runnable. It's in the memory, and as long as the CPU is allocated to it, this process can get into the CPU immediately and run its own instructions. So for this kind of processes, we call we name they are in the ready states. Okay, as long for the blocked state, it means these processes are unable to run until some external event happens. For example, if a process is waiting for another process get out of the critical region, then this process is blocked. Even though you allocate the CPU to this process, it cannot execute any instructions because it is waiting for an external event. It is waiting for another process getting out of its own its critical region. So this state is called blocked state. And there are four possible transitions among these basic three states. You need to understand how to analyze the transitions among the three basic states. And okay, you'll see the questions and you need to answer those questions based on these basic concepts. About the second topic, the semaphores, we need to know that semaphores has one semaphore has three parts. The first part is an integer variable, and this integer variable is used to indicate the number of available resources. It means if the semaphore is a positive value, then it means there are available resources in the system. And if it's a minus, if it's a minus n, if it's a negative value, then it means there are unblocked processes which are waiting for the resources. It means this N processes, they just requested the resources and there are no available resources for them. So they have to block themselves and they are staying in the waiting queue on this semaphore. So this is the meaning of the of the positive value or the negative value. You have to understand this first. Then you can try the two basic operations on semaphores. We use down operation to request a resource. And after you do the down operation on a certain semaphore, there are only two cases. Either you just the request is granted. It means you just get the demanded resource immediately. And in the second case, you cannot get the resource immediately because there are no available resources for you to use. So you have to block yourself and you have to wait for a while, and then some other process will finally wake you up and you can get that demanded resource finally. Okay, so this is the meaning of the down operation. And for the up operation, we use the up operation to return a resource. If a process just just finish its job, it doesn't need to use the relevant resource anymore. It needs to do this up operation on the corresponding semaphore. And after it returns this resource, the system might wake up a process if there is anyone in the waiting queue on that semaphore. So these are the basic concepts you need to know to answer the questions in the following exercises. So are you ready for the exercise? Because I just asked you to log in MOOC in advance. If you are ready, you can type 1 or anything in the discussion area, and then I'm gonna publish the exercises. Are you ready? You can type anything. Okay, so you'll have 6 minutes to finish these exercises. Okay, just submit your answers before the deadline. So here we go. 6 minutes, okay? Time is almost up. Hurry up to submit your answers. Okay, I believe the time is up. Let's come back to the class. If you cannot answer all of those questions, how to say correctly, it means maybe you haven't grasped these two important parts completely. So maybe you need to review with your textbook and the slides after the class, because these two parts are how to say it's they are uh, they are the most core concepts and core part for this course. So I hope you can understand uh, how to switch among these three basic states and combining with the concept of semaphores. You can understand how a process switch from this state to another state with the down operations or the up operation. Okay, so let's move on to the new content of this class. Um, for the IPC problem, we just say that there are three basic issues to be handled, right? The first two issues can be solved successfully with the semaphores, the mutual exclusion and the synchronization issues. Also, you can use the monitors to handle this issue, but we just don't discuss any details about the monitors. If you are interested in that part, you can check it after the class. And for the third issue relevant to the inter-process communication, it's about the message passing. It means for this part, it's comparatively much simpler than the first two issues, because we just need to we can just use two primitives to send the message to another process or receive a message from another process. You can see we just list these two primitives, and in the experiment, you need to use you need to how to say you need to analyze the code I'm gonna provide to you, and to see how the results and analyze why this result comes out from that segment of code. Uh, so we're gonna explain these two primitives before the experiment is before the experiment at the end of the around at the end of the October, I guess, because actually the first experiment is supposed to be finished in this week, in the third week. But as you know, because of the pandemic, we have to delay all the experiments. And by the way, the all the 4 experiments will be, I think, will be arranged around the end of the October, from the end of October to the November, around the 9th, from the 9th week to the 12th week, I guess. I'll let you know about the arrangements of the experiments, and I'll explain how to finish those experiments right before you get into the lab. And for those students who are abroad, you have to set up your own environment on your own computer, as I mentioned in the first class of this course, because you can't get into the lab in our campus, right? So that's about this message passing. We're just talked about this later, right before the experiment. Okay, so now let's move on to the next section about the scheduling, and this scheduling part is another essential an important part for this course, for this chapter. Because when we talked about the management of the processes, or when we talked about CPU management, it's basically relevant to 3 topics: the transitions among states, and the IPC problem, and the last one is about the scheduling. Scheduling. Okay, let's check the outline of these sections. First, we'll learn the brief introduction to scheduling, and you can see I just emphasize these 2 parts with the yellow color. We are gonna learn some specific algorithms to schedule in batch systems and for the interactive system. So after we learn this section, you need to understand, you need to grasp how to apply different scheduling algorithms to solve some scheduling problem. So if you are given a scheduling problem with some parameters, you should you should provide the final results about the scheduling. You should provide a completely scheduling plan, a scheduling scale. How to say, you should provide how to schedule for those processes and calculate some criterion. So this is you should put more effort and time on these 2 parts. And after that, we're gonna take a quick look about the last 3 parts about how to schedule in real-time systems. By the way, in this course, we don't introduce the specific algorithms for real-time systems. We just focus on the algorithms for batch systems and interactive systems, but we don't talk a lot about the algorithms in real-time systems. So if you are interested in that part, you can check it after the class. Also, we're gonna talk something about the policy and mechanism relevant to scheduling and the thread scheduling. Anyway, the important part of this section is the second one and the second part and the third part. But before that, you need to know some basic concepts about the scheduling. So, what is scheduling? The part of the operating system which is responsible for scheduling is called scheduler. So scheduler is kind of, you can view it as a special program, a special segments of code in the operating system, and this scheduler is responsible for selecting a process to run next, to run in CPU next. So, so how to select this process and where to select the process? I mean, you should select, there are multiple processes in the operating system. Some processes, they are in the ready state. Some processes, they are in the blocked state, right? So obviously, you need to select a process from all processes in the ready state, because as I emphasized, if this process is in the blocked state, even though you allocate the CPU to it, it cannot get into CPU to run any instructions, because it is not waiting for the CPU. It is waiting for for a certain external event. Maybe it is waiting for some input from the users. Maybe it is waiting for some signal or message from another process. So when the scheduler runs in the CPU, because scheduler itself is a segment of code, right? If it wants to select a process to run next, it needs to do this job by executing some instructions in CPU too. So when the scheduler runs some instructions in CPU, it has to know it only selects the process from all the processes in the ready state. So this is the first thing you need to know. And about the objects, I mean about the processes in the ready state, which are about to be scheduled by the scheduler, you need to understand we can roughly divide them into two categories. One is called computer-bound processes, and the other is called I/O-bound processes. They have totally different characteristics. We'll talk this sooner. And also, you need to learn when to schedule. So after we learned the characteristics about the schedule, about the objects to be scheduled, you need to learn when to schedule. I mean, when to call the scheduler to run in the CPU to select a process to run next. The time to run the scheduler is also important for the scheduling. And also you need to learn how some common sense about the scheduling algorithm. For example, you need to know that the scheduling algorithms can be divided into two types. One is called preemptive and the other is called non-preemptive. You need to understand the meaning of these two terms. And also you need to understand that the different scheduling algorithms are suitable for different environments, for different systems. As you can see in the outline, we have batch system, interactive system, real-time systems, different systems. They have different scheduling algorithm goals. They have different criteria to evaluate if this scheduling algorithm can perform well. So different different algorithms, they can be adopted by different environments because they just meet different goals from different systems. So that's basically all we need to learn from the first section or first part of this section. From this after I giving you this brief introduction, you need to understand the object to be scheduled, about the time to run the scheduler, and some common sense about the algorithms. So first, let's learn the two kinds of processes. So what is compute bound or compute intensive processes? From literally from the words you can figure out these processes, they just spend most of their time on computing. So you can you can imagine, or you can name some processes. You can find some examples which are compute intensive processes or compute bound processes. When you turn on the computer, you can do a lot of things on the computer. You just do those jobs by running different processes, right? So can you name any process which is a compute bound process? Or maybe let's just check the next type of the process, I/O bound or I/O intensive process. Maybe you can name example for this category easier. Okay, so this type of process means those processes which spend most of their time on waiting for I/O. So you can check these two kinds of processes through this figure. For the first one, the CPU compound process, you can see it just spent most of their time on computing, and after it runs a lot of instructions in the CPU, maybe it needs to get some input, or it needs to output some results. But this time is very short compared to the computing time in CPU. So this kind of process is called compute bound processes. A typical example about this process is compiler. You know compiler, right? If you are running a compiler, it means you need to compiling some source code into the machine code so that you can execute the program you just write. So if you are running a compiler, the corresponding process is obviously a compute bound process, because it just needs to it just needs to load the source code and the compiler, the program for the compiler into the memory, and it just needs to run a lot of instructions to compile them into the machine code, right? So for this kind of process, it's called compute bound or compute intensive process, because it just spends lots of time, most of the time, on computing. And for the I/O bound or I/O intensive processes, you can see it maybe it just run a couple of or how to say less than 100 instructions maybe, and then it needs to wait for some input or output to be done. So for this kind of process, the typical example is, can you name one? When you are using your computer, there are some processes which are typical I/O bound processes. Can you name one? For example, if you are writing some reports on Word, it is an I/O bound processes, right? Because it needs to, of course, it needs to run some instructions to format your input and to back up for the input. But most of the time is spent on waiting for the user's input, right? Because compared, yes, because we are using keyboard to type the words, type the characters into the word into the file, and it's very slow compared to the speed of CPU, even compared to the memory or hard disk. The speed to type on the through the keyboard is much slower than the speed in CPU or hard disk or memory. So the instructions they just need to wait for a long time to get the input from the users. So we can see compiler is a typical example for compute-bound processes, and Word is a typical example for I/O-bound processes. And if you know the difference between these two categories, you can understand sometimes why we scheduled for these two types of processes under some circumstances. So these are the this is the first topic we need to understand about scheduling, the two categories of processes. And next one, we need to learn when to schedule, when to call this scheduler, when to call this scheduler to run in CPU to select the process to run next in the CPU. Basically, there are four cases. There are four situations to run the scheduler. The first one is when a new process is created. After we learned in the learned something after we learned the process, the concepts about the processes, you can recall a new process is created, is always created by another process, right? And that process is called the parent of this new process. So after a new process is created by its parent process, a different operating system will have different different rules or algorithm to decide the next process to use CPU is the parent process or the child process. Because as long as you create this new process hasn't executed any instructions yet, and it's definitely after all the relevant data is loaded in the memory for this new process, it will switch from the new state to the ready state, right? So there is one more new process in the ready state. So maybe you should decide. Maybe the scheduler need to decide. Next one to use the CPU is the parent process or the new created child process, because both of them are ready for the execution. So this is the first case. And the second case is when the process exits. So if you recall the states, if you recall the life cycle of a process, it can be created and it's just make a lot of transitions among those three basic states. And finally, it can finish its job. Maybe it can finish its job and exit the system, right? Well, before it exits the system, it needs to return all the allocated resources back to the system. And of course, it needs to run some instructions to return the allocated resources. So it means when a process exits, before it exits, it's in CPU to run some instructions to return allocated resources. And after it exits, it means this process is no longer in CPU anymore. It just disappeared. There is no such a process. It just finishes its lifestyle. So it means at this time, after the process exits, the CPU is free. before it exits, the CPU is allocated to that process, and after the process exits, the CPU is free. When the CPU is free, it means it's a time for the scheduler to run. At this time, the scheduler need to get into the CPU to choose another process from the processes in the ready state, right? So this is the second case. And for the third case, when the process blocks, sometimes a process can cause some make some system calls to block itself, right? We just learned about this. We learned the sleep and wake up, these two system calls. In sleep, in this system call, the process can block itself. And with semaphores, if a process requests some resource, request a certain resource and there is no available resource for that process to use, then the process makes this down operation, it will be blocked too. So whenever a process block itself, no matter the reasons is for waiting for I/O input or the semaphore or some other reasons, as long as a process blocks itself, it means before the process blocks itself, this process is the current process in the CPU, is using the CPU, and after it blocks itself, the process will leave the CPU because its state is blocked state. It's not running state anymore. It cannot stay in CPU anymore. And it means now the CPU is available again. It's free again. So at this time, the CPU is available again. You need to call the scheduler and choose the next application process to run, to use the freed CPU, right? This is the third case. And for the last case is about the interrupt. When an I/O interrupt occurs, sometimes when if you record the part relevant to the interrupt we introduced before, you can see whenever the interrupt occurs, the CPU has to stop what it is doing, stop the current process, stop the instructions for the current process, and the CPU needs to handle this interrupt, right? Whenever the interrupt signal is emitted to CPU, it needs to handle this interrupt if the interrupt is not disabled. If it's not disabled, if CPU needs to handle this interrupt, and maybe this interrupt will require CPU to call the scheduler to choose another process. The typical example is this clock interrupt. After we learn some specific algorithms for the interactive systems, you can see in those algorithms, if this clock interrupt happens, it means maybe the CPU needs to check if the fixed slot allocated for the current process is up. If the time for the current process is up, then it means the scheduler needs to run and to choose another process to use CPU. So basically, these are four common cases to schedule. And after we learn this, after we understand this for possible cases, we need to learn more about the common sense of scheduling algorithms. I mean, you have to know this basic this basic concepts, basic terms relevant to scheduling algorithm. We divide it into non-preemptive scheduling algorithms and preemptive scheduling algorithms. For those non-preemptive scheduling algorithm, it means these algorithms just pick a process to run and then just let it run until it blocks on waiting for I/O, or it blocks on waiting for some event emitted by another process, or until this process voluntarily releases the CPU. So when a process will think about it, when the time that the process voluntarily releases the CPU, it might be the exit time, right? If this process just finish all its job, it doesn't need to use the CPU anymore. At this time, at this moment, this process might voluntarily releases the CPU, or if the process found that it needs to wait for something, it doesn't need to run any more instructions at a certain moment. It will block itself. After it blocks itself, the CPU just is available, and you can you can pick another process to run in CPU next. So these are the basic idea for the non-preemptive scheduling algorithms. So it means as long as a process is picked to use the CPU, it just leaves CPU voluntarily only when this process wants to leave the CPU, then the CPU will be available again. But for preemptive scheduling algorithms, no matter the current process in CPU wants to leave or not, the scheduler will decide that the current, the last process in CPU has to get out of the CPU and let another process to run next. So for preemptive scheduling algorithm, it means the current process in CPU might be forced to leave CPU, not voluntarily. Okay, so even though it wants to use CPU for a longer time, but it cannot stay in CPU anymore, because if we adopt preemptive scheduling algorithms, the scheduler has the right to force the current process in CPU out of the CPU. So this is the basic difference between non-preemptive scheduling algorithms and preemptive scheduling algorithms. Non-preemptive scheduling algorithms cannot force any CPU to get out of the CPU if they don't want to. But preemptive scheduling algorithms can do this. The preemptive scheduling algorithms have the right to push the current process in CPU out of the CPU, even though they don't want to. Okay, so after you understand this, we can talk about the next topic, about the three different environment or three different systems. Because in you can see for these three different systems, we are gonna adopt different algorithms, either non-preemptive or preemptive algorithms. For batch systems, you can see what's the essential characteristics for batch systems. If you recall the batch systems introduced in chapter 1, you can see it just needs to do a lot of jobs without with little interaction. For example, if you need to doing payroll, if you are doing the claims processing for insurance company, they just need to run instructions one after another to handle those transactions. They just need little interaction with the users because everything is on the program, everything is on the data. And for the batch systems, we usually avoid to switch process much more frequently because the process switches just cost a lot of overhead, and if we reduce the process switches, we can save more CPU time to run the real instructions, so we can improve the performance. Uh, because we are the basic idea is to reduce the process switches. So you can see the non-preemptive algorithms are usually adopted for this kind of systems. For batch systems, we usually adopt non-preemptive algorithms because we just need to know the results for a batch of jobs. You just for that batch of jobs, they just need to take turns to get into the memory and get into the CPU to run one after another. And there are they are most of them are compute bound processes. They need less interaction. They need less I/O operations, and so they don't need to switch a lot among the processes. And if we adopt non-preemptive algorithms, we can get better performance. And what kind of what performance is better for batch system? We'll see the criterion. We'll see the criteria for batch systems in the following a few slides. Here, you just need to understand most batch systems adopt non-preemptive algorithms. Of course, there are some cases that preemptive algorithms are adopted, but for this preemptive algorithm, usually it has long time period for each process. It means it won't let the process switch very frequently. Just let a process run maybe for a few seconds and then switch to another process. It's just waste a lot of time on switching. So if it adopts if the batch systems adopt some preemptive algorithms, it usually just adopt the algorithms with long time periods. And for the batch systems, in the second part of this section, we'll just introduce about three basic, and you can see two of them are non-preemptive algorithms and one is preemptive algorithm. So this preemptive algorithms and one is preemptive algorithm. So this preemptive algorithms can be adopted for batch system, but it and sometimes maybe it has better performance, but it depends. It depends on the concrete jobs running on the batch systems. So these are the are the things relevant to the batch systems you need to know. And for the interactive systems, usually we just adopt preemptive algorithms for interactive systems, because you can see interactive system, it just need a lot of interaction between the machine, between the computer and the users. So if the users input something, if the users type a command or just press some touch some icon, press some icons, it needs to get the response. How to say, not immediately, but in a very short time. It needs to get the response. How to say, not immediately, but in a very short time. You have to give the response to the user, the response to the users for interactive systems, because that's what the users expect. So if the users, sorry, something wrong is, yes, something wrong with my network again. So I have to set a hotspot on my phone. And now is everything okay? Can you hear me again? Can you hear me now? Because I think I just the network just didn't work a few seconds ago. Okay, now let's just switch to the hotspot. Okay, so I just talked about this interactive systems, right? So if the user type anything, the users will expect the immediate response from the computer. And how to implement this? It means the CPU needs to response needs to handle the I/O interruption imaged by the keyboard by the users. So it means it needs to handle the interruption by allow another process get into the CPU to run some instructions relevant to the input of that user. So you have to, the operating system, the scheduler has to allow some instructions, some process relevant to the input, how to say, replace the current process in CPU and get into CPU to run some instructions to handle those I/O, those input, right? So it means for interactive systems, the response time is essential. And of course, preemptive algorithms need to be adopted so that the request from the users can be handled in time. So this is about the interactive systems. You can see we just divide the algorithms into preemptive and non-preemptive algorithms. And here you'll see they are suitable for different scenarios, for different system, different environment. And for the last type is real-time systems. Some of you might think that real-time systems, it means some jobs have to be done, have to be finished before the deadline. So it sounds like we should take the non-preemptive algorithm so that the current process in CPU can finish its job. But actually, in the real world, the in real-time systems, a lot of processes they just need to run some instructions in a very short time. So after they just finish their jobs, they are gonna voluntarily leave the CPU. So for these cases, preemption is not needed, right? Because you don't need before if you just force a certain process out of the CPU, but that process might be handling some very important work. If that process is forced out of CPU, it has to wait for the next scheduling points, and maybe the next time when the process finish its job, the result is useless Because for the real-time systems, we can divide it into hard real-time systems and soft real-time systems. In the hard real-time systems, the deadline must be met. You must finish your jobs before the deadline. And for example, um, okay, let's just jump over the example part. You just need to know that for the hard real-time systems, the deadline must be satisfied, and for the soft real-time systems, sometimes, occasionally, you can disobey the deadline. You can, for example, if you are playing some music, uh, it's a typical real-time application, right? You have to listen to the music smoothly, and if the instructions are if you need to listen to the next second of music, and the data to be played is not decoded yet, then you can hear how to say, you can hear something which is which doesn't sound well. So it means, but for this case, even though you have bad experience, it doesn't cause any fatal results, right? But for some hard real-time system, if the deadline is not met, some fatal things might happen. Maybe you can check the example in the first chapter about the car manufacturing, and to see how it is why it is important for the hard real-time system to meet the deadline. Anyway, if you want in the real-time systems, usually the processes, they just need to finish their job in a short time, and they are gonna leave the CPU voluntarily, so you don't need to force them to get out of the CPU. Because if you force it to leave CPU, it might cause some fatal results, because you just push them out before they finish their jobs, and their jobs must be done before the deadline. After it's pushed out of the CPU, maybe you just make this process never meet its deadline. So this is about the real-time systems. But anyway, our focus is about the first two kinds of systems. I mean, batch systems and interactive systems. So for different systems or different environments, we have different criteria to evaluate if the algorithms are suitable for them. And when we learn this scheduling algorithm goals, there are some general goals for all systems, and there are also some specific goals for different kinds of systems. And as I said, maybe we just need to focus on the goals or on the criteria for the first two systems, batch system and interactive systems. So here we just list some general goals for all systems. It's about fairness, policy enforcement, and balance. And it's very easy for you to understand this criteria. For example, the algorithm should be fair, should provide fairness. It means you cannot allow a process keep using a CPU for a long time, which much longer than other processes. Each process in the system has the equal right to get a fair slot of the CPU time. So this is about the fairness. And the police enforcement means if there are some policies in the system, the scheduling algorithm needs to carry out this policy. It cannot disobey this policy. But policy is actually it's an abstract concept. You can check the example about the policy relevant to the safety in the textbook and to try to understand this part. But it's not so important. Actually, balance is somehow much more important criterion. Because in the computer, we are always trying to keep all parts of the system busy. It means you can't if there are multiple processes in CPU in the system. Some of them are CPU bound processes and some of them are IO bound processes. And for this system, usually they can get better performance than those systems have with only CPU bound processes, or than the system with only IO bound processes. I just explained this, meaning the difference between CPU bound processes and IO bound processes. You can see if the system have both kinds of processes in the system, if we schedule them in a reasonable way, the CPU can be the CPU and the I/O devices can be used or most of the time, right? But if the system has only CPU bound processes, it means the I/O devices are just idle for a long time. So if you have if we suppose if you have 3 CPU bound processes and 3 IO bound processes, maybe you need to load them all into the memory and let the scheduler keep the balance between these two categories of processes. It's much better than you just load 3 CPU bound processes into the system first. After these 3 CPU bound processes are done, then you load the next 3 IO bound processes into the operating system. You can see if you choose this way, the performance, we have a couple of criteria to evaluate the algorithms. If you choose the second way, then you can see the criteria is not they are how to say anyway, you can just get much lower performance, much lower values. So this is about balance. And for batch systems, for this spatial batch systems, we have some specific goals. Actually, it's just two. There are three. Yes, there are three criteria to evaluate the algorithms for batch systems. The first one is throughput, the second one is turnaround time, and the third one is CPU utilization. You can get different values on these three criteria if you apply different algorithms on the same on exactly the same batch of jobs, because the different algorithms they have different scheme to finish all the same jobs. But the most important criterion for you to understand is the second one, turnaround time. So when we learn some algorithms in the next part relevant to the batch systems, you can see we'll calculate the turnaround time of different algorithms on the same batch of jobs to see which algorithm can get a better turnaround time. And what does it mean by better turnaround time? The shorter, the better. So for the turnaround time, if algorithm A can get shorter turnaround time than algorithm B, then we can see for this case algorithm A is better than algorithm B. The shorter, the better. So what is turnaround time? Turnaround time is average time from the average means the average value of the batch of jobs. A batch of jobs consists of maybe 4 or 5 jobs, and each job will has its own turnaround time, and we need to calculate the average time from for each job. It has its own turnaround time, and this turnaround time is from the moment that this job is submitted until the moment it is completed. We'll see how to apply this definition, how to calculate the turnaround time in the next part through some concrete examples. So here you just need to remember this definition. The turnaround time means the time from the moment that this job is submitted until the moment it is completed. Okay, so this is the most important criterion we need to focus. We need to pay attention to, and for the first one, the throughput. The throughput, you need to know this meaning, know the meaning of this term too, because it's just a common sense for computer measured students. Throughput means the number of jobs per hour that the system completes. Of course, the higher the throughput is, the better the algorithm is. So you need to you need to complete more jobs per hour, right? Throughput should be higher. And for the third one, CPU utilization, it means you need to keep the CPU busy all the time. You should improve the CPU utilization by keep the CPU running, keep running all the instructions from cancel of jobs. But it's not so important, so we just jump over this part and move on to the next systems, the interactive systems. As I mentioned before, the response time is very important for interactive systems, because of course it should be shorter, right? The response time should be shorter, because as long as the user submits its request, no matter it's just the user tap it or the user click the mouse or touch the screen, as long as the user submits its request, the user will expect to get some response, get some results in a short time, right? Imagine you are using Word, and after you type a word, you type a sentence into the word, but nothing showing on the screen. You might be crazy about that situation, right? It's not acceptable. So you should shorten the response time for the interactive systems. That's the reason why we choose preemptive algorithm. Preemptive algorithm can ensure the requests from the users get handled compared to the non-preemptive algorithms. Of course, when we talk about this response time, there is some raw expectation on the response time because imagine you are using the computer to play a movie. After you double click that movie file, you know you need to wait for a few seconds to let the data and program being loaded into the memory and being decoded by the CPU, right? You know you need to wait for at least 1 second or 2 seconds to wait for the process to handle all the necessary behaviors. But if you are typing something into the word, you are expecting that the characters you just typed immediately showing on the screen, right? You don't expect you won't give the computer maybe more than 1 millisecond to show that characters off. So there are some how to say fixed or not fixed. So the users have their own expectations on the general response time relevant to different kinds of actions. So when the scheduling algorithm runs in the CPU, it needs to meet those expectations, right? Okay, so anyway, you can see the response time is very important for the interactive systems. But for in this course, we'll learn some concrete preemptive algorithms used for interactive systems. But you can see we just take the same criterion as batch systems. We just use turnaround time to evaluate the algorithm because it's hard to say it's hard to calculate the response time, the exact response time, because the users are not expecting the final result. Sometimes they just need to get some response first, and if you just keep outputting the results, you can output the results while you are executing some instructions to get the next output. It's okay for the users to get a result like that. So it's hard to simply calculate the response time. So we just use the same criterion. We use the turnaround time to evaluate the algorithms for interactive systems on this course. But if you are interested in about the some other concrete evaluation methods, you can check more materials on internet. So that's for the first two important systems. And for the real-time systems, we just mentioned that we don't need to focus on the specific algorithms. We just need to know that in the real-time systems, we need to meet or at least meet most deadlines. And you need to you need to control the processes in the real-time systems. You need to control them run in a predictability way. It means, for example, if you are playing music, the music should be played smoothly, right? So you need to continuously output the decoded data through on the speaker. So, but it can predicted, right? Because the data and the programs, they are generally speaking, they are comparatively fixed. You can evaluate the time to finish those kinds of jobs. So it should be predictable. It should be predictable, and um, and you just need to understand one important thing, that the deadline is very important. The deadline must be met in most cases. And here is an example about the if you miss the deadline, uh, and some fatal results will happen. For example, uh, we can imagine, we can suppose there is a device that produces data at a regular rate. So this device just produce some data at a regular date, and there is a process needs to collect the generated data. Of course, it should be it should the collection should be finished before some deadline, because if you the data just generates at a regular rate, it means at this point you have maybe 1 gigabyte 1 gigabyte data to be collected, and the next maybe in the next second or in the next minute you have another new 1 gigabyte data to be handled, to be collected. So if you cannot collect the last 1 gigabyte of data in time before the deadline, and then the next 1 gigabyte of data are already generated. If you cannot finish the last step of job, you cannot collect uh, the next new 1 gigabyte of data, and that data will just get missed. You lost a lot of data because you cannot collect them in time. You cannot collect those data before the deadline, and maybe the precious data just lost forever. So you can see in the real-time systems, it has strict limitation on the deadlines. It has strict criteria on the evaluation. Uh, so for this part, we don't need to uh, put more put too much effort. We just need to evaluate if this real-time systems can be scheduled, and how to schedule this issue. We just ignore it. So we jump over it. We just need to focus on if it can be scheduled and it's enough. Okay, so we'll talk about this later. The focus of this section should be put on the second and third part about the concrete algorithms relevant to batch systems and interactive systems. So here is our first algorithm learned which needs to be learned for this course. It's a very simple one. It's called first come, first served, and it's a non-preemptive scheduling algorithm. FCFS, first come, first served. So it means how does the scheduler select the process from the system? It just select the first come process. Which one arrives at the system first? Then that process will be selected. After this process is finished, the next process arriving at the system will be chosen and get the CPU to finish its job, and so on. So the processes are assigned the CPU in the order they requested. Here, the order they requested means the order they arrive at the system. So when the first job enters the system, it just starts to run some instructions immediately, and it can run as long as it wants to. So during this period, during the first job is using the CPU to run its own instructions. If any other jobs come in, they need to wait. They are gonna be put onto the end of the queue. There is a queue, and in the queue there are some jobs waiting to get into CPU to finish their jobs. But if the job when the for the non-preemptive algorithm, we know that they will leave CPU only when they want to, right? And when will the process leave the CPU voluntarily? Maybe after it finishes all job, it will exit, not only exit CPU, but also exit the whole system. And another occasion is to wait for something. If this process maybe it needs to get into its critical region, or maybe it needs to read something, or it needs to get some input data, or it needs to output some data, and then it doesn't need the CPU anymore, so it will block itself and get out of the CPU. At this time, the process will be viewed. This process just is like a newly arrived job and putting and it's gonna be put on the end of the queue. So that's the basic idea of HCFS. Pretty simple, right? After we explain the basic idea of the two non-preemptive algorithms for batch system, we're gonna illustrate how to apply these two algorithms to solve a certain scheduling program, the for FCFS and SJF. These two algorithms, you need to grasp them completely, okay? So, but today we don't have time to illustrate how to apply them. In next class, we're gonna show you how to apply this to non-preemptive algorithms. So in next class, I hope you can focus on this part, because we are gonna have the similar questions in the quiz. Okay, so this is the part for the next class. I mean, for the mid-autumn holiday, we are gonna change the time for the next class. Next class should be in tomorrow, right? So tomorrow afternoon, we're gonna take the next class, and in the next class, tomorrow, yes, we're gonna explain this, how to use this axis to solve the scheduling algorithm, how to solve this scheduling problem. Okay, so that's all for today. quiz is about after we finish the first 4 chapters. So it's not decided yet because we need to it's up to the time when we finish chapter 4. Okay, good. So that's all for today, and see you tomorrow.